We will continue now with the lecture on the response of materials to stress. Until now we looked at how we reach failure passing through the phases of elastic and plastic behavior. Now we will go on to see different types of stress strain curves and then start discussing brittle failure, and in the last part of this lecture we will look at failure that is occurring due to fatigue, creep and so on. So let us start by looking at some different types of stress strain curves. These are taken from the software that comes along with the book of Callister, and we see here on the top left the stress strain curve for cast iron, which is a relatively brittle material. We have hardly any linear elastic part in the stress strain curve, it is non-linear up to failure which occurs in a brittle manner. So cast iron is a metal which fails in a brittle manner, and we looked at the reasons for this when we talked about defects in the microstructure. We saw that flakes of graphite form in cast iron and these can propagate as cracks and cause failure. On the other hand, when we look at plain carbon steel on the top right, we see a curve where you have a sharp increase, that is the linear elastic part, the stress increases with strain, and then we have a flat part which is denoting the yielding, and then we have strain hardening with an increase of stress as strain increases. This would be the peak load or the peak stress, after which there is a drop in the stress and finally failure. These crosses mark the peak stress in each of these cases, just to give an indication of what are the stress values and strain values that we have for the different materials under uniaxial tension. At the bottom we have aluminum and titanium alloys. Both these cases you see that there is no definite yield plateau that we saw in the case of plain carbon or mild steel, but we have a smoothly increasing curve. There is a transition from the linear elastic to the final strain hardening and failure through a curved region. There is no definite yield point followed by a flat region and then strain hardening, but there is a smoothly increasing curve until the peak is reached, in this case of at about 500 megapascal, and then we have failure. This is for an aluminum alloy. For a titanium alloy, again the curve seems very similar, except that the peak stress, the maximum stress that the titanium alloy can take is about 1000 megapascals. The strain is also different, it is now 0.06 instead of what we saw in aluminum 0.17 was the strain at the peak stress. So we see that metals generally have a ductile behavior, in the sense that there is a lot of elongation, lot of strain before failure occurs. We see also that in alloys we do not have a very definite yield point. This is true for all polycrystalline materials, because different crystal grains will start yielding at different points. We also saw that a metal such as grey cast iron can have brittle failure, and that is the reason why cast iron is used in applications where we do not require a lot of ductility. In civil engineering application we use it for casting grills, fence posts and so on. Polymers also have a range of behavior patterns. At the top left we see a case of linear elastic and almost ideal brittle failure. This is in the case of bakelite or phenol formaldehyde, which was one of the first plastics to be used in large scale applications, and we see here that the stress at failure is about 50 megapascal, strain is 0.013, and I repeat that you see here a linear elastic response over a large part of the stress strain behavior followed by sudden failure. You do not have any substantial curve beyond the peak. On the other hand, when we look at the case of nylon on the top right, we see that there is a linear response followed by something like yielding, a flat part slightly increasing, we reach the peak at a strain of about 0.2 and then there is a gradual decrease and failure occurring. The stress is peaks at around 88 megapascal. So, this was very similar in shape to what we saw in mild steel. Rubber on the other hand does not have a yielding response that we saw in nylon, but what we have is a non-linear elastic response, in the sense that as we keep pulling, as we keep applying tension to rubber, there is a very high strain that rubber can take in the order of about 5 strains, and when we release the stress, the rubber returns to its original position, that is, there is no permanent deformation even though the strain values are very, very high. However, we also see that there is not a very large linear response, the linear response is very, very short, and after that we have a non-linear elastic behavior. It is still elastic because it returns to 0. When the stress is released, we return to the 0 point. So, it is still elastic, but it is non-linear elastic. In the case of high density polyethylene would be a material which has some amount of crystallization that increases the density, and this crystallization comes because of the ordering of the polymer chains, and what we have here is now a situation where there is an elastic part shown by this increase. We have a peak stress of about 23 megapascal. This is now where all the chains start being aligned in a certain section, and this is followed by a drop and some amount of plastic behavior, where the chains now start resisting load. So, you have a elastic part, a peak occurring, some amount of drop, this could be called softening, and then we have a plastic response over a large strain. So, we see that metals and polymers and many other materials have a range of stress strain behavior, and this has to be characterized and understood in order to be used in design. The stress strain response also changes with temperature. In this case, we have the diagrams for iron. The bottom curve is what we see for room temperature. So, this would be at normal temperature. So, we find that there is a certain yield stress at around 200 megapascal, then afterwards there is substantial elongation. With hardening we reach a peak around here, and then there is what is called necking, and then we have failure. So, the neck would form around where the peak value is. At a lower temperature, say minus 100 degrees, we find now that the yielding occurs at a higher value around 300 megapascal, and then again we have the strain hardening, the peak now occurs maybe somewhere around here, and then we have failure occurring at a strain of 0.4, which is less than what happened at room temperature. Now, if we decrease the temperature even further, when we go to minus 200 degrees centigrade, now we have a much higher yield value close to around 700 megapascal, but there is not much of elongation after that. Failure occurs abruptly at a very, very small strain. So, what we see here for iron is typical of many materials. As temperature decreases, we find that the strength goes up, but the elongation or ductility severely decreases. This is also seen in the case of plexiglass or a semi-crystalline polymethyl methacrylate, PMMA for short, and we find here this graph given by Callister showing the stress strain behavior again under tension over a temperature range of 4 degrees to 60 degrees. So, here the room temperature would be this case of 20 degrees. We find that PMMA has a relatively brittle behavior. You have a linear elastic part followed by slightly nonlinear behavior, and then PMMA fails in a brittle manner. However, if the temperature is higher, say 40 degrees, now you see that there is more nonlinearity, there is a decrease in strength from around 50 megapascal, it has come down to about 40 megapascal. The ductility or the elongation before failure has, however, increased. You have more strain until failure occurs compared to the 20 degree case. At 60 degrees, you have a significantly plastic behavior, that is, you have an increase, it reaches a peak value, and then there is a large plastic plateau which can go up to 1.3 strains. On the other hand, when temperature is decreased, if we look at 4 degrees Celsius, we find that the strength is higher, it exceeds 80 megapascal, but then after that the failure is very brittle. So, just like we saw in the case of iron, we see here that as temperature decreases, strength increases, but ductility or elongation to failure decreases. So, in general we find that modulus of elasticity and yield and tensile strengths decrease with an increase in temperature. Significantly, ductility increases with an increase in temperature, or it decreases when the temperature drops, that is, the material becomes more brittle as the temperature drops. Now, we talked about ductility and brittleness. How do we quantify these concepts? We can do so based on the stress strain diagrams that we looked at, and we can say that a material is ductile if there is a higher energy absorbed until failure occurs, given by the area under the stress strain curve. So, this curve A, C prime, B prime can be an indication of how ductile the material is. If the material is not ductile, like we saw in the case of grey cast iron, bakelite, the material fails in a brittle manner. This area now A, B, C is much lower than what we saw for A, B prime, C prime, and therefore, we can say that this material which fails, like in this case, which has a stress strain diagram A B instead of A B prime, is more brittle than this one. So, the area under the curve is an indication of ductility. Another indication could be the elongation up to failure. You can see very clearly that A C prime is much more than A C prime being that of a ductile material, A C being the elongation up to failure for a brittle material. So, ductility can be defined as a measure of the deformation at failure. It represents how much a material can deform before failure occurs, how much energy can be dissipated or absorbed by the material during failure. It can be defined in two ways: percentage elongation given by the difference between the initial and final lengths divided by the initial length, that would give the elongation, can be put in terms of a percentage, or we can look at percentage reduction in area, that is, we look at the cross section, change in cross section area divided by the initial cross section area is given as a percentage reduction in area, which also represents ductility. Other than this, we saw in the previous figure that the area under the curve can also be treated as a measure of ductility. So, how does ductile failure occur? What happens after the strain hardening phases and the ductile phases? How does the material actually fail? If we take a specimen under tension of, say, a metal, and we look at failure that is dominated by dislocation movement, we would have a specimen like this subjected to tension, This is what is usually called a dog bone specimen, where there is a section with a lower width where failure would occur, so that we can monitor more easily, and which is also far away from where the specimen is gripped. So, here cavities would form as the dislocations start moving. These cavities link to form a crack. This crack now grows 90 degrees to the applied stress. This crack now grows laterally in this case, and then as the crack reaches the ends, we have slip occurring at 45 degrees, which is the direction of the maximum shear stress, and we have now a curved failure occurring like what is shown here. We have the crack joining together with an inclined slip plane around the circumference if it is a circular specimen. So, when we look at a photo, we see something like this. So, this is in the case of aluminum. This part is where we had the flat crack propagating, and then we have the slip zone over the edges. So, you see that there will be a jagged edge around the ends instead of a smooth surface. That is where finally we have the slip ending and fracture completing. This is called the cup and cone fracture, this being the cone and this being the cup. So, this is very typical of ductile failure in metals. If we take a closer look at the failure surface, we will see dimples that have formed during the ductile failure. Dimples are depressions that form on the failure surface. Now, these dimples or cavities initially start the flat crack, and then we have propagation, this is the slip zone, and we have shearing occurring, and finally fracture. In the flat crack part, we will have round equiax dimples, and in the slip zone we have these dimples more oval. That is, if we look towards the center of the bar, we will see a dimple like this, okay, and the dimples point towards the origin of failure. So, this is the center of the bar where the failure started, and the dimples form with this orientation, and this is now what is called the shear lip, where shearing occurred, and this is where the oval dimples are formed. If we look closer in a scanning electron micrograph, say in the case shown here, which is annealed 1018 steel, we find in the flat center we have equiaxed dimples. So, these are all equiax, almost circular dimples. This is now in the flat area, and here in the shear lip we find elongated dimples. The dimples are now elongated. So, these are depressions which form, and this cavitation leads to the propagation of the crack and ultimately failure. So, this is what happens during the ductile failure of a material such as steel, and we ultimately have a lot of strain that the material can undergo until this final failure occurs. Failure in a ductile manner does not have to occur only under tension. We can have even materials failing in a ductile manner under shear. If we take the case of a bolt that is holding together the flange of an I section and say a tie, suppose we have this tie pulling on this bolt and the bolt transferring the load to the flange of this I section, we have this force now pulling, and this is transferred as shear stress to the bolt. The bolt now undergoes a shear stress, and if the stress is very high, if the load is very high and consequentially the stress is very high, the material can shear, and here you see this picture from the book of Gear, that you have a very high strain here caused by the shear force, and you have yielding occurring here. So, this would be the yielding zone in shear. Some other materials also exhibit ductile failure, that is, the failure is not sudden, but it is a gradual type of failure, and one example is the compression failure of wood, say in a strut. If you have a piece of wood like this, vertical lines that you see are the grains or the fibrous material. And what happens is, when you have very high compressive stresses, these fibers at a certain point kink and you have something like a shear zone forming. Across this zone, if you look at it closely, you will see that the fibers of the wood are kinking, are bending like this, and you have ultimately a zone of shear forming. So, along this line the fibers are bending, the wood fibers are bending, and when adjacent fibers all bend together because of this high shear occurring in compression, you have this slip zone forming in wood, and this gives rise to a ductile failure. The failure is not sudden. In the case of polymers, a very interesting phenomena occurs which causes something like strain hardening in the polymer. Suppose we take a thermoplastic polymer. This would have long chains entangled, and if we take a coupon made out of this was the dog bone specimen that I mentioned earlier. So, imagine that we apply a tensile force here, we are going to pull on this, and failure is going to occur here because this is where we have a reduced section, and in this section if we were to look very close, we would see the polymer chains all entangled, long polymer chains, say in a linear polymer. There is random orientation of the polymer chains, and when we apply stress, necking occurs as we saw in the case of metals. Now, here when the necking occurs, these polymer chains now all elongate, they are all stretched, leading to the decrease of the cross section, and when they all stretch, now we can see very clearly that they would take much more stress than in the case of a polymer system which has chains all entangled. So, this system now will take more stress than this, and therefore, it shows strain hardening type behavior, or we see an increase in the polymer strength as the strain increases. So, we have talked about strain hardening. Strain hardening now is the phenomena that makes a ductile metal harder and stronger. We will talk about metals basically, even though we saw just the slide earlier that polymers can also strain harden. However, strain hardening is a phenomena that is very important in the behavior of metals, in how metals can be used effectively and how we can make metals stronger through strain hardening or cold working. So, strain hardening, as I said, is a phenomena or a procedure which makes a ductile metal harder and stronger as it undergoes plastic deformation. This is called work hardening also, or cold working. Cold working because it is carried out, this occurs when temperature increase does not accompany it, that is, it is occurring at room temperature or ambient temperature. So, that is why it is called cold working, and the degree of plastic deformation or the percentage cold work can be expressed as the change in area of the section divided by the original area as a percentage. So, this is called the percentage cold work. So, if we take a bar under tension and we look at how the cross section area changes, the change in area divided by the original area is expressed as the percentage cold work, an indication of how much strain hardening the material undergoes. What we find is, when we cold work a material, as the cold work increases, the yield and the tensile strengths increase. However, the ductility decreases. So, we have in the next two slides curve showing what I have just told you about the effect of the cold work. On the x axis we have the percentage cold work. This, you remember, is defined as the ratio between the change in cross section area and the original area. In the plot on the left, we have yield strength as a function of the percentage cold work, for copper, brass and steel, and we find in all the cases we have an increase in yield strength as the cold work increases. That is, due to strain hardening we have an increase in the yield strength. Now on the right we have the tensile strength, that is the strength at failure. This obviously is higher in all cases than the yield strength, but we also see the same trends where the tensile strength now increases as the percentage cold work or the effect of the strain hardening increases. More strain hardening, higher are the yield strength and the tensile strength. On the other hand, what we see is the ductility decreases. On this graph on the left we find that as the percentage cold work on the x axis increases, we see that ductility now decreases. As we strain harden the material, we cold work the material becomes less and less ductile and more brittle. Now Callister has an interesting diagram which I have shown on the right, which explains what happens in terms of cold work and the stress strain behavior. Now let us look at this first graph, which would be the stress strain behavior without any cold working. So if we take a material such as mild steel, we have an elastic part, an yielding part, then we have a strain hardening, necking occurring and failure. Now suppose I was to increase the strain until I reach say this point and then I unload. Now if I consider this as a new material and I was going to do a tensile test again, the stress strain diagram would start from this point. I would have an elastic response up to this, yielding would occur here, followed by necking and failure. This is this curve. What I have just described is what will happen in this curve. This is a cold work material where a certain amount of cold work has been done, and now when this cold work material is loaded, it has an elastic response, yielding, and it continues with the previous stress strain diagram. However, this elongation is now less because we have used up some of the plastic deformation when we did the cold working. Now suppose I were to do this again with the original material, but I stop at a later point, I go up to here and then I unload. This new material, if I test it again, will start from here, go up here, this would be the yield point, then it would reach a peak and so on. So that would be say something like this, that would be something like this. Here I would have a large elastic regime followed by yielding, and immediately I have necking occurring and failure. So we see that the higher up I go before unloading, more cold working I will have, higher will be the yield strength because I am taking the material to a higher stress before unloading, but the elongation starts decreasing drastically because I am using up the plastic deformation capability of the material. So when we look at cold work, as the cold work increases, the strain capacity will decrease, but the tensile stress capacity will increase. This is the reason why we had the phenomena that we discussed earlier. So strain hardening in the microstructure can be explained as occurring due to the interactions between dislocations or dislocation strain field interactions. Dislocation density increases when the deformation or cold work increases, dislocations start moving and coming closer to each other, and there is more interference between the dislocations, and this will cause a hindrance of the motion of the dislocation. We have seen that when grain boundaries hinder dislocation movement, we have an increase in the strength, in the yield strength. Similarly here now, as dislocations start moving and interfering with each other, we have an increase in the dislocation density, and therefore we have strain hardening or an effective increase in the strength. The stress needed to deform the material now increases because of this higher density of dislocations, which comes about by the increase of cold work. We can remove this effect of strain hardening by a process called annealing, which is heat treatment. We will discuss this in a moment. So, we can have a material which is initially not strain hardened, we can strain harden it, and through a heating process we can anneal it. So, this means that when we apply heat to a strain hardened material, we can reverse the effect of strain hardening to some extent. This is annealing. This is the reason why we should be careful in applications where we use strain hardened materials. We should not subject them to heating through welding and so on, because this can bring down the strength that we have achieved by strain hardening. So, annealing is a process by which the properties and structure of a cold work metal can revert back to the pre-cold work state, that is the original state, by using heat treatment. Remember that strain hardening is done at ambient temperature. Now, when we anneal it at higher temperatures, we bring the material back to the original state. Annealing consists of 3 stages: recovery, recrystallization and grain growth. Recovery is where most of the residual stresses are made 0, they are compensated. Recrystallization is where new crystals are forming, and grain growth, as the name implies, means that larger grains are forming. So, this is a nice diagram which shows all the different phenomena in one graph, where we have along the x direction the effect of temperature applied going through the 3 phases that we looked at in text: recovery, recrystallization and grain growth. First, let us look at the top what happens due to the temperature during annealing. First, we see that in the recovery phase, the internal residual stresses that were brought about by the cold working decreases drastically initially during the recovery stage. The hardness and strength do not change much. Ductility starts to increase, and mainly what happens in the grain structure is now we are releasing some of the residual stresses. The grains start recovering from cold working. In the next phase, more sustained temperature, we find new grains starting to form. The residual stresses are now completely gone. There is hardly any residual stress remaining in the material, and this coincides with a drastic drop of hardness and strength. So, hardness and strength have come down significantly, whereas ductility continues to increase. In the microstructure, we find now that the residual stresses are gone and new small crystals start to grow within the structure. In the last phase, the grain growth phase, we have now no residual stresses, ductility has come back to the original pre-cold work state, as well as hardness and strength. Grains now start to grow, that is, instead of the small grains we have larger grains. This yellow line shows the grain growth. So, larger grains now form, less grain boundaries and larger grains now occur. So, to look at it again, recovery is a low temperature heat treatment needed to eliminate residual stresses that we have introduced during deformation during the cold working. Recrystallization is a medium temperature heat treatment which eliminates all the effect of strain hardening that were produced during cold working. Grain growth is where through diffusion we make the grains larger, we move out the grain boundaries, and therefore, there is a reduction in the amount of grain boundary area, and the system also decreases the energy and becomes more stable. These are some pictures, some photo micrographs taken from Callister showing different stages of recrystallization and grain growth in brass. In this diagram we have a cold worked brass, 33% cold working, and you see here many of the slip planes. In the different crystals we have all the slip planes that have occurred due to cold working. This is now just after cold working. When we start annealing, say 3 seconds of heating at 500 degrees Celsius, we find recrystallization occurring. This small imperfections which are starting are actually crystals which are starting to grow. We see a decrease of the slip lines being prominent, and we have the small crystals now growing. This is the initial stage of recrystallization. Now we continue. Now after 4 seconds at 500 degrees centigrade, we have the cold worked grains being replaced by recrystallized smaller grains. Recrystallization completes at 8 seconds at the same temperature of 580 degrees. So we hardly see any slip planes, and we see a lot of small crystals in the picture. After 15 minutes, now the grains have grown, there are larger grains, these different colored areas are individual crystals or grains. Now after 15 minutes we have a different grain structure than what we saw before. Now finally we have a stage where we have grain growth at a higher temperature, 700 degrees 10 minutes, and we find now that the grains now are larger than we saw before. Grain growth is significantly more. We have larger grains, fewer grain boundaries, and therefore we have a system with less potential energy or lattice energy. So these are the different stages of annealing. We can put both the phenomena that we have recently discussed together, cold working and annealing, in the same picture. We take the case of an alloy of copper with 35% zinc, and we will see what happens during cold working to the different properties, and then what happens when we anneal the same after it has been cold worked to 75%. So on the left side we see the cold working part. On the y axis are the different properties, on the x axis initially we have the percentage cold work. So this would be the starting point where we start off from, no cold working, and we see that first as we cold work, this is now the cold working, as we cold work up to 75%, there is almost a linear increase in the tensile strength. If now we start annealing it, in the recovery phase we hardly have any change in the tensile strength, and then there is a drastic drop in the recrystallization and grain growth phase. Elongation on the other hand, as we increase the percentage cold work, decreased, elongation decreases as we saw before, the material becomes less ductile and more brittle. When we start annealing, again initially in the recovery phase we do not see much change, but then afterwards we see the ductility and elongation increasing. This graph is that of grain size. We found that in the process of cold working there is no change in the grain size, neither do we find anything happening in the recovery phase of annealing, but then afterwards we have in the recrystallization the formation of tiny crystals. There is a sudden drop in grain size, and then we have larger grains growing. In this plot we also have electrical conductivity, which decreases slightly due to cold working, and we recover that as well during annealing. So these are the different processes that occur during cold working and annealing. Now what happens when we have brittle fracture? We had looked until now at failure that is ductile, dominated by dislocation movements and yielding in metals. We can also have cases where the failure or the fracture is brittle. Brittle means sudden without any large deformation occurring, and the crack propagation is very fast. Here we do not have a cup and cone type of failure. Suppose we look at the failure of a rod of material failing in the brittle manner, but we have a crack that is flat. The crack runs across in a flat manner and we have now the sudden failure. So, if we have brittle failure, these are pictures showing brittle fracture in mild steel, we will have a crack running perpendicular to the direction of the tensile stress. In this case, the tensile stress is applied in this direction. We will find that the crack occurring perpendicular to it and finally a flat fracture surface. What is interesting is that some materials have a ductile to brittle transition, that is the same material under some conditions fails in a ductile manner and in other conditions fail in a brittle manner, and generally this is dominated by temperature effects. So, as temperature decreases, we find that many materials change their failure mode from ductile to brittle. This transition occurs over a range of temperatures, it does not occur at a fixed definite temperature, but there is a gradual change over a range of temperatures. In metals, what we find is that FCC crystal structured metals, for example aluminum and copper, remain ductile even at low temperatures, that is there is no ductile to brittle transition over a very large range for FCC metals, while BCC and HCP alloys experience this transition from ductile to brittle transition. So, it also occurs different ways in different metals, not all of them are the same. This is the reason why we have to study and examine when the ductile to brittle transition occurs. We also find that some ceramics and polymers also experience a ductile to brittle transition. Now, these are some quotes regarding famous failures that can be attributed to ductile to brittle transition. This is a quote from this link given here, disastercity.com, on the sinking of the Titanic. I will let you read through it. Basically what it says is that when the Titanic failed, there was not enough knowledge about this ductile to brittle transition. A similar ductile to brittle transition also occurred in the failure of the Liberty ships. Over 5,000 Liberty ships were produced during World War II without taking into account this phenomena of ductile to brittle transition. About 1,000 of these failed between 1942 and 1946 because of low temperatures, and 200 had severe fracture again between the period of 42 to 52. The government thought that something was wrong because in the colder North Atlantic there was more failures than in the warmer South Pacific. Until 1947 this remained a mystery. Then in 1947 a ship broke into two in the Boston harbor in the cold conditions, and this was evidence that it was temperature that was breaking the ships and it was not necessarily the German submarines. These are pictures where we see the ship breaking into half, this you see is the crack occurring. So, this gave rise to this major studies on ductile to brittle transition and change in design of ships and other elements. Ideally, we have fracture occurring with the pulling apart of bonds in neighboring planes. However, we will see later on with more detail that real materials fracture at tensile stresses that are much lower. This is the problem. The failure under fracture occurs at strengths that are much lower than the theoretical tensile stress that should occur when interatomic bonds are broken. The theoretical stress is about 2 orders higher than the actual failure under fracture. This difference was attributed by Griffith in the 1920s to the presence of defects or tiny cracks which always occur in different materials. We also find that surface cracks are more effective in causing fracture than internal cracks. So, surface cracks, if they are eliminated, will help bring down the brittle fracture. The property that governs this resistance to crack propagation is called fracture toughness. These are concepts that we will examine in later lectures. Fracture can now occur through grains or along the grain boundaries. When fracture occurs across the grains, it is called transgranular or cleavage fracture, like we see here, where we have the grains failing. This is the transgranular fracture. Then we have cracks that can pass through the interfaces. This is called intergranular fracture, cracking along the grain boundaries. Finally, a comment on how to protect against such brittle fracture occurring. The most important methodology is to treat the surface. If the surface is free from defects and defects do not occur during service, then the brittle material is better protected. There are two ways how surface treatment has been done in materials such as glass. One is etching, say with hydrofluoric acid, the surface layer is removed along with the cracks that occur in it. Consequently, the etched glass now, since it does not have any defects on the surface, has a higher strength than the unetched glass until some abrasion or scratches occur, and this can be prevented by covering with a resin on the surface. On the other hand, again with glass and other materials, we can induce a compressive stress on the surface which prevents the tensile opening of the cracks. That is, the crack is prevented to open on the surface, the defects are kept close by pre-compressing through process like tempering, ion exchange, so that the cracks do not start opening from the surface. So, these could be different methods of preventing surface defects from becoming cracks and causing brittle fracture. So, to summarize, we have looked at different types of stress strain behavior. We have looked at how the cup and cone failure develops, which is typical characteristic of ductile failure under tension. We also looked at how brittle failure occurs with sudden cracking, and we have closed this part of lecture 7 by looking at surface treatments, underlining the influence of the surface defects. In the next part of this lecture, we will look at phenomena such as fatigue and creep which lead to failure, and here again failure occurs at stresses that are lower than the strength of the material, and they occur sometimes in a brittle manner. That is why we are concerned about such type of failure. Thank you.